In this video, I want to introduce fast Fourier transform. Fast Fourier transform is actually not an new transform, but only an efficient algorithm for computing DFT. So I want to introduce two FFT methods. The first one is decimal in time domain. So we let xn be a sequence of lengths. The length is the power of 2. Then we split xn into two subsequences. The first subsequence is the even indexed points in xn, and another subsequence is the odd indexed points in xn. Then we can write xk equals to the summation of n from 0 to n minus 1, xn times omega n to the power of nk. So this is just the DFT formula of xk. Then we can write x as the summation of the even indexed points in xn and the odd indexed points in xn. Then then we can write omega n to the power of 2kl, because omega n equals e to the power of minus j 2 pi by n. So we can so omega n to the power of 2kl can be written as we can move 2 here to the denominator in n, then we can write omega n to the power of 2kl as omega n over 2 to the power of kl. So we can rewrite xk equals to the summation of L from 0 to n over 2 minus 1 times the even points in xn times omega n over 2 to the power of kl. Similarly, we can write the odd indexed elements here. So in this way, we actually write the n point DFT. So xk here is an n point DFT, and actually we write the n point DFT as the sum of n over 2 point DFT, because this sequence is an n over 2 point DFT, and this sequence is just the n over 2 DFT times a complex number. So using FFT, we actually convert the n point DFT to the summation the summation of n over 2 point DFT. So we can use a butterfly network to represent this formula. So for example, if we want to do an 8-point DFT, so we first split the sequence in time domain to even indexed points and odd indexed points, and we do the 4-point DFT, and we get J0 to J3. Then we can use J0 plus H0 times omega 8 to the power of 0 and get x0 here. And because omega n to the power of k plus n over 2 is can be written as this, and because omega n to the power of n over 2 is actually -1, because omega n equals to e to the minus j2 pi by n, and if we omega n to the power of n over 2 is equal to e to the minus j2 pi times n times 2n. This is just e to the power of minus j pi, and this is cosine pi minus sine minus j times sine pi, and this is -1. So we can write here actually x4 equals to, but using this formula, x4 equals to j4 plus h. So x4 is actually j0 plus h0 times omega n4, and omega n4 is equal to omega n is equal to minus omega n0. So we just use omega n0 times -1 to calculate the x4 here. So let's talk about the complexity of the FFT algorithm. We know in DFT, xk equals to n from 0 to n minus 1 xn times omega n to the power of n. So for each k, we have n multiplication and n minus 1 addition. So for all k, because there are totally n k in the frequency domain, so totally the complexity is all n square. But for FFT, we can split the n point DFT here further to the 2-point DFT. So there are actually log n stage in the algorithm, and in each stage we have n multiplication. Because we only use omega 8, because we only use omega n k here, and omega n k plus n over 2 can be represented by the omega n k. So the multiplication is n over 2, and the addition is n. So the complexity of FFT is O n log n. So this is an efficient algorithm. Another fast Fourier transfer I want to mention is decimation in frequency. So this algorithm, we also use the length of sequence. We also assume the length of sequence is n, where n is the power of 2. Then we split the signal in frequency domain to the odd index and the even index sample. So here the odd index is x2k equals to n from the summation of n from 0 to n minus 1 xn times omega n to the power of 2nk. Similarly, we can convert omega n 2nk to the omega n over 2 to the power of kl. So so we can rewrite x2k equals to the summation of n from 0 to after we rewrite the omega here, then we split the summation of xn here to the we split it into the first into the summation of the first n over 2 points and the last n over 2 points. So the first summation is n from 0 to n over 2 minus 1, and the last summation is n from n over 2 to n. Then we rewrite n in the last summation. We get this formula, and then because omega n over 2 to the power of kn over 2 is actually 1, because this is because omega n over 2 is equal to e to the minus j 2 pi over n over 2. And if we multiply this formula here, we get minus j 2 pi n over 2 times kn over 2. So this is actually minus j 2 pi e to the minus j 2 pi, and this equals to this equals to 1. So we can rewrite x2k, which is the even indexed points in frequency domain. So we can rewrite the even index subsequence to the DFT of n over 2 points, and the element is this one. Similarly, we can rewrite the odd subsequence as similarly as the DFT of n over 2 points. So we can also use butterfly network to represent this formula. So here we firstly, so for the odd index, so for the even indexed elements, we first add the xn and xn plus n over 2. We first add this two element to get this point, and this point. Then we do the n over 2 point DFT and get the even subsequence of xk. Then we compute the xn minus xn plus n over 2 in time domain and get this value, this value, this value, and this value. Similarly, we times the corresponding omega n. Then we also do the n over 2 point DFT, and we get the even subsequence of xk. So this is the decimal in frequency, and the complexity is actually the same as the complexity using decimation in time domain.